The energy that buildings are using is mostly used for heating and cooling air, and this is not done in an optimal manner in most residential building situations. So there is a huge opportunity to manage and improve the way buildings consume energy over time. So the cooling and heating units and any other energy recovery devices that are used to treat the air that's pulled into the building are known collectively as the heating, ventilation, and air conditioning system, or HVAC system. So the HVAC system has to treat the air that's coming into the building, and it has to do this in the face of many disturbances to the indoor environment conditions. Specifically, changes in occupancy, weather, and solar radiation, lighting, computers, and other equipment all change the indoor air temperature, and the HVAC system has to deal with this. There are also a variety of energy sources that buildings can draw from, and storage options as well for buildings to use. And all these energy sources can fluctuate in price and availability. So not only do buildings account for 40% of energy use, in the summer the majority of this happens during the late afternoon, and the most used source is electricity from the grid. The grid could operate much more efficiently if instead of having to deal with this peak load, there was a relatively constant demand throughout the day. So this raises the question, when exactly should we be using and storing energy from each of these available sources? So the building energy management problem is a natural candidate for optimization. However, because of the size and complexity of mathematical models associated with buildings, these calculations are difficult to perform in real time. So as chemical engineers, why do we care about this problem of optimizing building energy use? And the answer lies in the nature of the problem itself. If we focus on the building, we can regard it as an integrated plant that converts and recovers energy from a given set of sources, and it's subject to disturbances in operation, mainly from the environment and occupancy. On a closer look, we can see that the energy recovery, which is used to pre-cool air that's coming into the building and reduce the amount of cooling needed in the summer or heating in the winter. So this energy recovery entails a feed effluent heat exchange, and mixing of exhaust air with fresh air streams is the same thing as material recycling. These are fundamental similarities with integrated chemical processes, and we can therefore translate concepts used for designing a control and real-time optimization system for chemical plants to apply to buildings. So in a few minutes, I will outline a proactive energy management strategy that will take advantage of the availability of forecasts of occupancy and weather and other disturbances, and a dynamic model of building behavior to predict what is going to happen to the indoor air temperature. We need to perform a model reduction process to be able to perform these calculations online and in real time. And I will show a simulation case study and then discuss some experimental work that we are planning to undertake. So we'll begin with a prototype building system. This is a picture of the Thermal Facade Lab here at the UT School of Architecture, and it's a unique facility originally built to test the impact of different building materials and structural designs on building energy use. The Thermal Facade Lab is also therefore equipped for making detailed measurements of temperature and energy use, and also has a configurable HVAC system. So we're taking advantage of this setup to evaluate different control methods, effectively combining static design features and dynamic function. To begin designing an energy management system for buildings, we have to model dynamics of building energy use and its effect on indoor temperature. So the models I'll be showing here today are based on the Thermal Facade Lab, but they will still be applicable to many buildings. Here's a schematic of the Thermal Facade Lab. Instead of modeling every wall and surface, we have a single mass that represents all the structural elements. And the structural elements are in contact with the main building zone. A zone does not mean a single room, though. Zones in buildings are defined by a mass of air that is handled using the same HVAC system. So residential homes are typically single zone structures. And this means that our model of the Thermal Facade Lab will be applicable to any single zone residential home. Other important features here include the presence of a heat recovery ventilator that recycles energy. So this device, again, facilitates heat transfer from hot outside air to cool exhaust air in the summer to pre-cool the air and reduce the amount of cooling that has to be provided by the air conditioner. There's also dampers in the ductwork that regulate the airflow rates. And we're only considering 2 disturbances in this model for now, occupancy and weather. And this is going to be on a typical summer day, so we're only concerned with cooling loads that have to be satisfied. The on-off controller that you see measures the zone temperature and turns the air conditioner on and off as needed. And this is a very typical control method used in residential buildings. And it leads to usually inefficient or not optimal energy consumption. So we are going to replace this on-off controller with a model-based control system. This new controller will supplement measurements of the zone temperature with forecasts of weather and occupancy before making decisions on how to operate the air conditioner or air handling unit. A model of the building is used to predict the evolution of the air temperature over time within the optimization. So here's a block diagram of the thermal facade lab that highlights the energy or enthalpy flows throughout the system. There is an energy recycle loop, again, because of the heat recovery ventilator. This is in addition to inlet and outlet flows. So if you imagine a perfect world where the outdoor air temperature is a constant 25 Celsius and the temperature suddenly increases to 30 degrees, what will happen to the zone and structural elements temperature? Do they change quickly or slowly? The zone temperature actually does both. There is an initial fast increase in the zone temperature and then a very slow approach to the new steady state value. And the structural elements temperature changes slowly over the course of several hours. So this multiple time scale dynamic is well documented empirically in buildings, and it's a concern for us because it's difficult to use a single control system for variables that evolve in this manner. Convention is to design separate controllers for each time scale. So we'll begin to quantify these multiple time scale dynamics by defining some dimensionless numbers that capture the behavior of our system. The first, epsilon 1, is the ratio of the thermal inertia of the air to the structural elements. And the second dimensionless number is the enthalpy of, compares the enthalpy of the input stream to the enthalpy recycled in the heat recovery ventilator. We know that both of these numbers will be less than 1 for the buildings that we're looking at because the density and heat capacity of brick and concrete and all the other materials that make up the structural elements is much larger than that of air. And we've installed this energy recovery device because it's going to be operating efficiently. So it will be recovering more energy than is being drawn into the system. So with this knowledge, we can write a model of the rate of change of various temperatures in the ducts and elements of the thermal facade lab. Here I'm showing the ODE for the rate of change of zone air temperature and the structural element temperature. So notice how the dimensionless numbers appear in this system. They're reciprocals, and 1 over a small number will, of course, be a very large number. So these parameters have a large influence on the rate of change of temperatures in the model. This is exciting because the mathematical model can explain the multiple dynamics observed in buildings, and we can see that the multiple time scale behavior is due to the discrepancy between the air and structural elements thermal mass, and also because of energy recovery. I also should have mentioned before that rigorous first principles models for buildings also pose numerical issues for optimization when solving, and models of this form are typically stiff and are difficult to solve from a numerical point of view. This model form is also known as a singularly perturbed system, characterized by the presence of small parameters. And this is a general form of all model where theta is now a vector of different temperatures in all the streams in the thermal facade lab. So I want to provide some background on singularly perturbed systems before beginning to analyze this model. Our model is in non-standard singularly perturbed form. And in this case, all the state variables will exhibit a fast transient, which is shown in red in the phase portrait, followed by a slow approach to steady state. And this is obvious, so in the phase portrait, where we see this fast transient that approaches a equilibrium subspace. And once the states are within the equilibrium subspace, they evolve slowly towards the final steady state. So there's plenty of mathematical theory for singularly perturbed systems, but most relevant to our situation is a model reduction process that isolates the behavior in each time scale. Basically, we can derive separate models or equations for the fast and slow dynamics shown here. So again, here is the general form of our model. And we begin by looking at the equation for temperature and the thermal mass, or the structural elements. And these will be the slowest dynamics of our system. To look at the faster dynamics, we define a new time scale, tau1. And this is effectively zooming in on the fast time scale or stretching the original time scale to look at the fast transient. So when we do this for the equations for air temperature, we obtain a model that is still in non-standard singularly perturbed form. So we again define another time scale. So we're now zooming in on the air temperature time scale to see the fastest time scale in the system. And we can use this to define an intermediate time scale. So within this intermediate time scale, we see that it's a differential algebraic equation system. So the fast time scale is at steady state. We have 0 equals g of theta. And the intermediate time scale is based on tau1, or the temperature of the air in the system. And this DAE system is a one-dimensional state space realization of the air temperatures throughout the thermal facade lab. So what we also notice here is where exactly our manipulated variables appear in these equations. U is only affects the temperatures in the intermediate time scale, tau1. So buildings are slightly more complicated than the initial non-standard singularly perturbed example I showed, because we obtain 3 time scales in the model reduction process, not just a fast and a slow. Because of the presence of energy recovery, there is an emerging intermediate dynamic behavior that's physically associated with the total thermal energy contained in the air throughout the building and HVAC system. So it's not just the air in the zone. And the key insight here is that the control actions preferentially influence the intermediate time scale. So this is what we want to control and use in the optimization. So the intermediate time scale will be our reduced model that we use for the building system. With this reduced model, we are now in a position to test the model-based controller. We've already, so the results I show will be for 2 different cases: minimizing energy cost and tracking a set point for indoor air temperature and this is going to be performed in a nonlinear model predictive control framework. Again, the model that we're using is the reduced model for the intermediate dynamics. And this model should be non-stiff, and there's also only 2 states associated with it, instead of having to consider the temperatures for everywhere within the thermal facade lab model. So this also reduces the complexity for the optimization. Because this project is still in its initial stages, we want to establish that it will work before performing experiments at the thermal facade lab. So as a proof of concept, we performed simulations on a more detailed building model. And these results are what I'll be showing here today. These are the disturbance profiles for the simulation. I want to point out that hour 0 here corresponds to 5 a.m. So the temperature increases during the day and peaks around 2 in the afternoon and then decreases at night. And there's also 2 people entering the building or entering the zone during normal working hours. And there's also a large increase in cost during the period of peak energy demand. And this is very realistic for summer in Austin, because the market price of electricity can be up to 40 times higher during this peak time compared to the price in the morning or overnight. These are the results for the simulation focusing on tracking a set point temperature, and there is really good tracking. The small spikes that you see are because of the disturbances in occupancy occurring at those hours, and the reduced model does not give an exact prediction of the correct zone temperature in response to the occupants. So this is eventually corrected through the feedback control that is still present in the control scheme. The total cooling provided is shown in the figure on the right, and again, more cooling is required when the occupants are present and as outdoor temperature increases. The more interesting results are in the case for energy management and minimizing cost. The bounds are set in the MPC are set here so that the upper bound is the same as the tracking set point. So the results for tracking effectively are the same as the results would be for minimizing total energy use in this framework. For cost minimization, we see a pre-cooling behavior before the cost increase occurs. So the optimization is choosing to reduce the zone temperature to the lower bound for a period of time in order to further cool the structural elements so that when the cost increase takes place, we can rely on the walls and floor and furniture to act as a heat sink and effectively keep the air cool without the air conditioner doing as much work. And this saves money for the HVAC system operation. And the effects seen here are a bit small, so I mean that the temperature rises really quickly once the pre-cooling period, once the air conditioner isn't doing extra work to keep everything cool. And this is because the thermal facade lab does not have anywhere near as much thermal mass as a large home or office building. So these effects would be exaggerated in a more practical settings. But we do still see a cost savings, and most importantly, all these calculations were performed using the reduced model in real time on my regular desktop computer. And I should point out too that if I were to use, so the plant model in this case was a more detailed model of the thermal facade lab, and if I were to use that model in the optimization, so there would be effectively no plant model mismatch, the calculation time effectively doubled, and it was taking the calculations weren't done within the sample time. So the reduced model is very useful from a computational point of view. So we've accomplished a lot here. We've seen that the empirical knowledge, or the empirical observations of multiple time-scale building dynamics can be justified theoretically using singular perturbation theory. And non-stiff, low-order, control-oriented models can be derived, again, using singular perturbation theory for the dynamics in each time scale. The NMPC framework can result in significant savings. And again, there's a very simple implementation here and real-time execution that's a result of using the reduced model. There's a very large market for this type of control system, mainly for buildings in the southern region of the US, because again, here these are all climates similar to Austin, which are the weather models that we used for our simulations. The model is also very portable. We can, because of the format with the structural elements and single zone, we could change, and it's still a first principles model after the model reduction. We can use different parameters for different buildings to test this model on more than just the thermal facade lab. So I want to thank everybody from the UT Department of Civil and Architectural Engineering for their help and support with us using the thermal facade lab, and the Pecan Street project here in Austin and Smart Grids IGERT. And also the AICHE CAST division, who is going to be supporting me showing this work at the conference in 1 week in Pittsburgh. So thank you, everybody, for listening. If there's any questions, I'd love to answer them right now.
Okay, well, let me start off with one question, and then
Sure.
I'll open it up to others who might have questions as well. Again, I'll just say, unmute your microphone if you'd like to ask a question. So you mentioned, what was your sampling time on your controller?
20 minutes.
Okay, 20 minutes. So it took, when you used the forward model, it took upwards of 20 minutes or more to compute the optimization?
Yes.
Okay.
Yep.
And then,
hour.
sorry, what was the horizon on that controller?
Oh, 8 hours.
Oh, 8 hours. Okay. Okay. So you had about 24. Let's see, about 24 moves into the future where you had to decide where to run your cooling system. So you see that model reduction is really a key enabler for using these models. What kind of thoughts do you have about scaling up to buildings with multiple zones?
So these ideas would translate directly. So you can scale the model that Kara developed for a single zone to a building with multiple zones. And you preserve, the main advantages here that you preserve physically meaningful structure to the model, so it's much easier to port this model to a different building. So we're operating, so the building industry is, I'm not sure if the folks that are in attendance realize it. It's a very cost-driven environment. So essentially, nobody makes money from a building other than rent. So they're driven by cost reduction, and the cost of implementing any advanced optimization or control solution has to be as low as possible. The idea is to make sure they're able to replicate one implementation and as many others as possible.
Okay. Well, good. Any other questions? Rishi, it's good to see you were able to join. We haven't spoken in a while. Rishi, when he did his PhD studies, he worked on economic MPC. And so, Rishi, what are you up to now?
Hey, John. Yeah, it's good to hear. Good to be back. Well, I've always been here, never got a time to join into one of these webinars. I've been following the schedule online and through the group post, but yeah, I'm glad I was able to get online into one of these webinars. And it's really good that you guys are doing this, and gives us an opportunity to look at these things, what's going on. I'm familiar with a couple of Michael's talks from COECCC, but yeah, it'll be good to see some more talks here. So yeah, I mean, I did economic MPC back when I was doing my PhD, and it is really nice. In fact, this seems like a good application that you want to test that out. And I know Jim's still working on looking into more applications rather than the 30 that we worked on when I was back at UW. But it's really, what we found out was the real benefits actually depend from application to application. And energy management is one of the key areas that I think is going to show significant benefits, especially if you're trying to use a good model, because that's really the key. If you have a good model, you can take advantage of doing an economic optimization only if your model is good, and doing a model reduction, trying to preserve your structural information or physical information in the model would really tap into those benefits. So yeah, that's good.
Good. Well, thanks for your comments, Rishi. And where are you working now?
I'm with Shell.
Shell. Okay,
yeah,
great.
I'm in Houston. Yep, not too far from Austin.
Very good.
Well, you can always come and pay us a visit.
Yeah, sure, definitely.
Jeff, I wanted to get your perspective on this as well. You've been working with industrial model predictive controllers for quite a while. Can you give a perspective of some of the size of problems you guys are able to solve at Honeywell with some of your technology?
Well, my first comment about this is I like the concept of the reduced models. A lot of the problems that we've had commercializing nonlinear control and optimization has been due to the complexity of the models. I mean, John, we were on projects together, and getting polymer kinetic models and things like that and making them solve online reliably is challenging. I like the idea of the simplified models capturing the important nonlinearities. That was one of my questions actually, was what is the configuration information you need if you want to develop a model for a building? Do you need to calculate the mass? What are the, how have you abstracted the building? I saw some of the slides, but I didn't really catch, what are the key input parameters? And then that's the other thing, is there one of the keys to making them successful in industry is to be able to calibrate them in real time as you measure things and find out your predictions. You can correct with feedback, but you can also update the model predictions, update parameters that will give you a better long-term model as you're going along. So, and it's really nice if some of those parameters that you're estimating have a physical interpretation. So, I guess, that's my perspective. I like the simplicity. I don't think you can do everything with linear models, which, I like to see, incorporation of some nonlinearity where it's important, and finding that optimal level of complexity is the key to making it successful in industry. Right now, it's too difficult to put, partial differential equation models of a building online. It's doable, but it's not going to catch on and make a lot of money, I think.
So Jeff, we really want to for those comments. I think they reflect the basic tenets and the thoughts behind this work. So to answer your question, that I switched, or Kara rather, switched to slide 11. I'm not sure if you can see it.
Yes, I can.
So there's certainly the physical parameters of the building, which are mass, heat capacities of the material, volume of air. They all play into this, and they can all be determined from a blueprint of the building. Heat transfer coefficient can also be estimated from stationary models that are available. But like you mentioned, there is a mechanism. Actually, she hasn't talked about it, but she has some very interesting results that account for plant model mismatch. And basically, there is a disturbance model that's built in that gradually eliminates offset. So we are able to do offset-free tracking in nonlinear MPC with this mechanism.
Right. That's a good feature, because if you have a good way to model these buildings that's not overly complicated but captures the essence of the structure, then you could utilize these models for pure performance monitoring, and you could show that your predictions were tracking what the building was, actually when you measure things. So it's a good way to justify putting it on the system online.
Yeah. I mean, that was a very exciting result, and it's, I think, for the first time that a lot of these concepts have been developed for linear MPC, but this idea of disturbance modeling in a nonlinear context has been a little more elusive.
Very nice. I like the work.
Thank you.
Yeah, it's very good. So you'd classify these models as more semi-empirical then? So you have some first principles elements in it where there are dependencies on mass of the building or other things, and then more simplified equations that describe the energy content in the building. Is that right?
I would actually say they're not semi-empirical. They're first principles through and through. because the reduction doesn't entail any sort of data-driven set or model identification. So you can with a mass and energy balance, and will end with a mass and energy balance, except for it's written in a different time scale and in a transformed variable, but both the time scale and the variable itself remain physically meaningful. So this sort of plays into one of the biggest fear factors, or counters one of the biggest fear factors rather in the building industry, which is that operators will kind of see a black box and lose sort of the understanding of what your controller does. By preserving this concept by preserving physically meaningful variables, I think it's another powerful argument for selling or implementing this kind of approach.
Yeah, well, I agree. I think that you can extrapolate a lot better. And as you mentioned, one of the nice things about that is you can take your controller technology and apply it to other structures as well without a lot of identification work. So that's very nice. Okay, so hold on. We had Kai have a chat question. He doesn't have a microphone. His question is, can you say something about the current state of the art for office building systems?
Yeah, so that's a good question. They are a little more sophisticated than your regular home, where on-off control is the state of the art. Office building systems are easier to modulate in the sense that there are more degrees of freedom, because at least where is Kai based? I would guess Germany.
Come on, he just chatted. He's a postdoc at MIT.
Well, let me address the first question, and then if something else comes in on the chat pipeline, we can take those questions. So, commercial buildings are a little easier to modulate because cooling is done at an external chiller station, and then the zones themselves are cooled with cold water. So the same tenets would apply, but you have a little more in terms of degrees of freedom. You also have a little more in terms of disturbances, because occupancy varies more significantly during the day.
Well, one more question. Alex just chatted in. Very interesting work, Michael. I missed the beginning of the talk, though. How did you incorporate forecasts?
So forecasts are sort of a natural part of the nonlinear MPC framework. Right? When you do optimization, you can account in your future steps. You can account for predicted values of different. These are available. So occupancy schedules, and certainly you can obtain electricity prices are usually set by contract. These are available and very easily incorporated into nonlinear model predictive control, or model predictive control for that matter, as exogenous inputs into your calculation.
Okay, great. Okay, and then just a follow-up question from Alex is there uncertainty in the forecast?
In these calculations, not. We haven't, well, in these calculations there isn't, but you can accommodate uncertainty, and one of the directions we're looking at is to be able to have a average profile that the calculation is based on, and have a integral control time count for unmeasured.
Well, if there's no other questions, let me thank Kara and Michael again for presenting. And you know, I thought it was very interesting talk. And if you'd like to hear more from them, they're going to be presenting at the ASEHE meeting in Pittsburgh in just I guess about a week. Is that right, Michael?
That's correct. We also have a couple more presentations regarding stochastic optimization of complex systems, so you're more than welcome to attend those. They're going to be on, one of them is on Tuesday, one of them is on Thursday, both of them within the CAST division.
Okay, great. Okay, well, thank you, Michael and Kara, and we'll go ahead and sign off now.